Can you hear me? Okay, great. Hi, good afternoon. The topic of the talk is multi-vendor interop specification review. First of all, I'm Soin from Artisan Embedded Power. And in summary, this is the work the team has been doing over the last year and a half, where we started with the interop and turning that work into a specification. So that's the topic and the end goal of this interop study. So here is the agenda. So I will start with the interop objective and the challenges. Then we will look at the key challenges that have been addressed in the past, and then focus on particularly for, that went back. And in this session, we will look at how we come up with the interop process outline that is required for the different vendors to work together to cooperate to facilitate interop. And then the interop specification review and the document we have come up with, we will go over and review that document. And more importantly, this work is based on ORV2 specification. That was, this was sort of an afterthought because ORV2, we had the samples and then we went to do the interop. So again, we have a process in place and we want to take that process and apply it to ORV3 as we move forward. So at least we have a building block to apply it to ORV3. So that's the agenda that we will be following on this one. So essentially, what is interop? Interop is to allow PSUs and the other components like PowerShelf, BBUs to work together in a system and be compatible and make sure there are no issues. So that is the end goal. And the real purpose of this is to facilitate multi-vendor interop. So we can take the pieces from different vendors and have them function seamlessly, and so there is no issues. So that's what we started off with. So as we all know, when we look at the design from different suppliers, everybody could have different approaches to their design. So when you look at electrical challenges, everybody designs, different vendors will have different approach to the current shear circuit. So they will design their current shear circuit differently. When you look at the control, the dynamic response, they will use different components and they will have different behaviors. And that goes, if you use different topologies, the power supplies will come up at a different time. And especially when you put two power supplies together, you could run into challenges. Just talking on that one, when the power supply shuts down and how it restarts, the restart behavior could be different for different power supplies from different vendors. And talking on the same thing, when we look at the firmware, when we look at the control and the monitoring, this extends there as well. So, in a nutshell, these are the electrical challenges that we deal with. Moving on in terms of mechanical, dimensions is one thing. When you look at the power supply dimensions, we could all specify dimensions in a different manner. And especially if you don't follow the same way of specifying dimensions, you could have problems when let's say you insert a vendor A into the shelf, and then you insert the vendor B into the shelf, and there could be issues. Same applies for latches, the pin length, and if you use the connectors from different vendors, there could be compatibility issues. And moving on, if you put two power supplies together, they have the same color green, and the intensity and the specification there, that plays a part as well. So in a nutshell, finally, the thermal part is another thing. We could have thermal issues as well if you don't pay consideration to that. So essentially, these are all the challenges the team faced when we started off with this work. And we have to thank David, who actually from Facebook, he actually provided us the guidelines for the interoperability of the mixed supplier PSUs in the rack power shelf. And this is in the wiki, this document, which sort of laid out the guidelines. How should we be addressing this from the vendor base? So the expectation from a customer point of view. So here is an example. What I'm trying to show here is a simple example as one of the key challenges that we all face and how we went ahead and addressed this. So if you look at this circuit here, what we are showing here is this is the output stage of one power supply from one vendor. This is from another vendor. They would have a different voltage loops. They would have different current shared loops as well. So what we expect is all these things to work together. And if you have two, three, or four vendors, you could imagine the complexity. This could be hundreds of components in a current share circuit. This influences your current share, your dynamic response, and all the things that are tied up with that. So we expect all these to work seamlessly together, and when the two units are plugged into the shelf. If you look at the next slide, what I'm trying to show here is what could possibly happen if we don't pay attention to this. In the top left-hand side, this is an example of if the load dynamic change is slower than the current share bandwidth, we can get into the oscillation, and there is a master power supply and the slave power supply. They could keep on swapping their roles. And on the right-hand side is when the load dynamic change is faster than the current shared loop bandwidth, the other power supply could keep on pushing the voltage up till you get into saturation mode. And this is where the third case, when the voltage feedback loop of master power supply is slower than the slave power supply's feedback loop. And this is the fourth case when it's the reverse. So in a nutshell, even if we follow the rules, okay, the power supplies have to share and everybody designed without having certain criteria, we could run into a lot of instabilities. So without proper consideration, we could run into instability. So this was one of the first tasks that the Interop committee addressed last year, and we presented this result actually in Amsterdam last year, where, okay, here we are. Okay, so we presented the results last time where if we put, the conclusion of this study was if the dynamic load response is lower than the settling time of the current shared feedback loop. Anyways, that was the result, and all this is summarized in the website with all the previous studies that have been done in the past. So in a nutshell, these are the challenges that have been addressed in the past. We have addressed the electrical challenges, current share, and dynamic response. Peak loading is another challenge when power supply is loaded to 120% of the load. I'm giving an example of ORV2, 120% of the load and 170% of the load. And if you don't pay attention, power supplies may shut down. So that was peak loading. Same thing for mechanical challenges. And for thermal interoperability, the purpose here was to represent the power supply as a PCD or a power conversion device, so that the power supply from vendor A could be replaced by a power supply of vendor B. So what needs to be done here? So all that work we will show in the next slides how that translates into the spec and what we need to do to address that. So okay, so let's say we have addressed all these issues. So what is the next step? How do we go ahead addressing it, working with different vendors, and how do we do this? The first and the foremost step of this thing is that we need to execute a multi-vendor NDA. So where we have to sign a joint NDA between the different PSU vendors and the customers so that we can exchange information freely. So what needs to be done is that we need first step is we need to define the power supply, the specifications which are beyond the power supply spec. So this will go beyond the spec for Interop. Then the next thing is we need to cooperate with other suppliers to exchange some information, because just merely supplying information is not enough. We need to have certain information transfer, and I'll cover that when I go to the spec part. Then we take that information into account, and then we go ahead with the design. Team does the design, and then we perform additional analysis and tasks. And finally, and the most importantly, we define and execute test program. So this test program has to take the power supply from multiple vendors, They could be put in a rack in different positions. If you have 4 positions, position A, we got to swap those. And not only that, then we need to set these PSUs at different extremes. One could be set at the maximum input voltage, one could be set at output voltage, one at the lowest input voltage, steady state, dynamic response, fault conditions. So we have to define that. So if you can look at this program, which we did for this example, is 1,000 pages. And this could only be done on an ATE. So we have to define these cases, execute on an ATE. So that's, in essential, the whole thing that needs to take place. So based on this, I'll just open up the document which we came up with. Okay, I hope this works. Okay, so this is the first Interop specification. And if you look at the index of this, just want to look at the time. So if you look at the index, so we have the specification definition, information exchange and design analysis, testing and execution phase, right? So this is the content that I described in the messages. Just I'll go into briefly into detail. So I touched briefly on specification definition is we need to define the specs. Then we need to do exchange information, and I'll get into detail what we need to exchange at this stage we have agreed on. And in testing stage, we need to test at steady state and dynamic conditions, startup condition, shutdown, hot swap, fault simulation, temperature effects, corner cases, roll swap. So this is the real testing that needs to happen. So in terms of specifications, so I walked you guys through the example of the current sharing case. So what do we need to do is, so in a nutshell, we defined that if we set the bandwidth of the PSU to this range, so all the vendors follow these guidelines, phase margin, voltage loop bandwidth, we set the limit for the bandwidth, and we set the limit for phase margin. At the end, what it does is it lays the framework that the PSUs, there's a less chance of an error when we test these PSUs. I'm sorry, this is not an easy way because I'm working with a Word document here. This was another thing we discovered, that the dynamic loading, in this case, we need to not only define, we need to define the droop. It is understood this will be part of the spec. What a power supply spec doesn't have is the special cases, like you go to 120% of the load and the power supply is supposed to work there for, I believe in this case was 20 seconds. When you go to 170% of the load, we need to work for 3.3 milliseconds. So we need to define the droop that goes above the power supply spec so that all the vendors are in compliance with this. And if you do this, there's a fairly good chance that the amount of errors we will see in the interop will be much lower, and we will cut down the time to market and the time we lose in testing and all the stuff that that happens with the interactions. And finally, just looking on the mechanical aspects, I touched that earlier on this. It's really important that we all follow the same consistent standard. Whether it's ISO or ASME, we follow the same standard. All the vendors have the same data points, right? And we don't use terms like min or max specifications. We clearly specify what those dimensions are. So because we have seen issues when you put one supply, the other one doesn't fit, one has to struggle, and we can avoid all those issues which result as a result of not paying attention to these things. In connector types are really important because connectors from different vendors may be identical, may have certain tolerance issues, and they may not exactly fit in the same manner. Latches again is another thing, material and finishes. So I don't want to go into detail, and there's also issues on the mechanical loading as well. I just want to touch briefly on the thermal side that this was really a lot of work. This was presented at San Jose meeting earlier this year. So when you look at the PSU, right, for the power supply, what's really important is that we define the PQ curve of a power supply. So we're going to need help from a good collaboration, not only from our customers, but also from the different vendors to work together to define the PQ curve of the power supply. And what's also important is, what is the worst case of a PSU is when the PSU works at a maximum load and minimum input voltage. That is again a worst case, and that is really important that we define that as well, because that would decide what happens at the rear of the power supply where there is components in the shelf in the back. So we need to take care of that as well. So that is an example, and again, this is just what the study is, and if there is more input from the team, that will really be helpful so we can make this document better and make it, more suitable for ORV3 as we move forward with this. Then we look at the power shelf again. In the power shelf, we need to have power shelf PQ curve. What power shelf PQ curve does is it sort of determines what is the back pressure for the power supply. So we define that as well. In addition, we define the minimum available airflow versus load and maximum temperature versus load. So if those conditions are there, so this lets, you can treat the power supply as an interchangeable unit from a thermal perspective. So that would help as well. And finally, I talked about the information exchange, that what we need to do and when we need to do this. So like I said earlier, this for ORV2, we started Exchange doing this once we had samples in place, and that was last year. We had ORV2 samples, we went with Interop, we did it, and we learned a lot during that testing. And we want to avoid those mistakes for ORV3. So what we do is, the goal here is that all the vendors have the independence of designing the power supplies. We do our own design, and once that design is once we're at the paper design, we don't go. Oh, this has moved up a little bit. Just a second. So once the paper design is complete, we share these things for electrical side. I suggest we share current share circuit. I've had discussions with Lighton and others, but again, we will have to agree on what we all agree on sharing, or whether there is a subset of that could be shared. I share profile, Drew profile. So once you do this, we won't have issues on current sharing. Peak load response, it's really very difficult to characterize that in electrical terms. So we need to understand from different vendors what is the behavior under those conditions on paper. So then same thing goes for rise time, transients, unit shutdown coming up. So we take all those things into account, and on the communication side, we have CAN interface detail, Modbus implementation details, analog signals, power supply PQ curve, and the thermal shelf PQ curve. So once we exchange those, then we can go ahead and build the samples. So this is done before team goes ahead and builds the samples. So this will ensure the early learnings and all these things can be taken into design as much as possible, so we minimize the churn to the samples when we build them. So ideally the samples will be much, much better, and there's a much better chance to succeed at Interop. So that's been the work done to date by the team, and this is the summary of all the work and the recommendations from the team. So the next step, and before this document goes to the committee, would be to put the testing process definition and execution phase, which is defining the test cases, what we learned. Like in the case of ORV2, there are 3 shelves, vendor A in different positions, what are the different swaps necessary, the corner cases, things of that nature. And then this will become a spec which could be applied, taken further to ORV3, and then we can apply it to ORV3. So that's that, and I'll just jump back to the presentation and summarize. Okay, so what I've presented is the work that the team has done so far, the 1.5 years of experimentation, all the details, all the testing that went through, and then how that translated into a draft spec moving forward. So And I like to the teams to have a look at the spec and see if there's any input we can get, and we can incorporate that into the spec so we can make it better for our next generation of ORV3. So I guess that's where I conclude my talk. Thank you.